The following is fall 2011 Math 227 Test 3, number 4 in my test, or in Melanie's test this will be number 8. An NAPA auto parts supplier wants information about how long car owners plan to keep their cars. A simple random sample of 25 car owners result in mean of 7.01 years. So this is the sample mean of 25. That's 7.01, and standard deviation of that 25 simple random sample is 3.74. Now assume the sample is drawn from a normal distributed population. Part A, find a 99% confidence interval estimate of population mean. Okay, so the confidence in level will be 99%, and we want to find the confidence interval for the population mean. Okay, now let's start with the critical value, the C equals 2 for 99%. I hope we all remember for 99% that is 2.575. Okay, if we do some little imagination, which what are we doing here? This is if this is the standard normal distribution or normal distribution, this is 99% here, so this is 0.5%, and this is 0.5%. Okay, or 0.005. Now when you look at the table, you will see that the negative C equals to negative 2.575. Therefore the positive C will be 2.575. Now let's use that. Okay, now the margin of error, therefore the margin of error will be 2.575 times, oh hold on, I think I made a big mistake, a very big mistake. I should not use the C distribution. Because the standard deviation given to us is the standard deviation of the sample, right? So I will be looking at the T distribution. Okay, we will be looking at a T distribution. This is 99%. Okay, now the T distribution, this is negative T and positive T here. This is 0.5%, and this is 0.5%. Now when I look at the T distribution, here's my T distribution. If I look at my T distribution, right, the degree of freedom is 24, and then the area in two tails is 1%. Okay, the area in two tails is 1%. This is 2.797. Okay, so this will be T equals to 2.797 instead. Now what I'm showing you here is actually the common mistake happened in the actual test. You need to be able to differentiate and remember that the standard deviation you have is the standard deviation from sample, not from the population. Therefore, what happened then, when you do computation for the critical value, you need to know that you're using T, not using Z. Okay, the margin of error equals to 2.797 times the sample standard deviation, 3.74 over square root of 25. Now here I will compute that. 2.797 times 3.74 divided by 5, the margin of error will be 2.09216 if I round to 5 decimal places. Now therefore the 99% confidence interval for mu will be given by is 7.01 minus that margin of error less than mu, or you want to use equal to, that's also okay. 7.01 plus 2.09216. Okay. On the left hand side, I will get that's 4.91784 less than mu less than 9.10216. Okay, but that's the confidence interval for the population mean. Now, I hope you see the mistakes that I made. Okay, the given is the sample standard deviation, therefore I will not use Z distribution when I try to find the confidence interval for the population mean. Now let's move on. Part B. Find a 99% confidence interval estimate for the population standard deviation. Now, if I need to do standard deviation, means I need to do the variance first, right? Okay, then the formula, the 99% confidence interval for the population variance is given by the degree of freedom, which is 24, times the sample variance 3.74 square, big over, let me write down, so it's a chi square right less than sigma square less than 24.3.74 square over chi square left. Now what is the left right for the chi square? This is chi squared left and this is chi squared right. Now notice the difference in order. Okay, now if this is 99%, then this will be 0.5%. 0.5%, and the one here is 0.5% as well. Okay, now let me grab my chi-square distribution table. If I want the area to the right is 0.05% with degree freedom 24, I will get 45.559. This is 45.559, and the chi-square left for the area to the left is 0.5%, means the area to the right is 99.5. I will get 9.886. 9.886. Now, try to check with your table. Okay, now then I will put the number in. This is 24 times 3.74 square over 45.559 less than sigma square less than 24 times 3.74 square over 9.886. Okay, 24 times 3.74 square divided by 45.559, that will give me 7.36852, which if I do the square root later on, I will get, this is later on 99% confident interval for sigma, that will be 2.71450 later on. This is for sigma, this is your sigma square. Okay, let me go on with the right hand side computation. Divided by 9.886, I get 33.95735, and then when I do the square root of that number, I get 5.82729. Okay, now I get the 99% confidence interval estimate of population standard deviation. Now, part C. If several years pass and you want to conduct a new survey to estimate the mean length of time that car owners plan to keep their cars, how many randomly selected car owners must you survey? Assume that you want 95% confidence that the sample mean is within 0.25 years of population mean. So the question here basically, we want to estimate the mean length of time that cars owners want to plan to keep their cars. Now the question is how many n. The confidence level that we want, okay, and then the margin of error is 0.25. Okay, now the question is we need to find what is the n. The problem is we don't have the population standard deviation, right? We only have the sample standard deviation. We have the sample standard deviation to be 3.74. Okay, so what can we do? This is what we'll do. We will assume this is our population first, but population standard deviation. So according to the formula, n equals to the ceiling of C critical squared times the sigma squared over margin of error squared. Okay, now that's what we assume first, that this is the population. We assume this is our population standard deviation. So that will be now the critical value for 95%. That's 1.96, I believe. Right. 1.96, and then I use this 3.74 as my temporary number. Over the margin of error is 0.25 squared. Okay, so 1.96 squared times 3.74 squared divided by 0.25 squared. That will give me the ceiling of 859.76, which means I will use 860 data now. But notice that this is our temporary number. Let's try to match it with the t. Okay, with the t, then let's see, we want 95%, right? Right now assume we have that the 5 decimal places, I mean 5%. I will use 500 for now. Okay, if I use 500, will this give me the margin of error which is less than 0.25 if I use this number? Okay, if I use that number, will that give me? So it's like the checking, will this number reasonable, will this 860 be reasonable for our as the number of data. Let's see, then it will be the following. The margin of error, we want this to be less than 0.25, equals to 1.965 times 3.74 over square root of 860. Will this give me a number less than 0.25? If it is yes, then we'll use that number. Okay, 1.965 times 3.74 divided by the square root of 860. I get this is 0.2506. you see that it is not, right? Okay, now what you can do, you increase the number. Okay, even though I think it may not be necessary, because that 860 is very close to 1000 already, and that's 1.962 instead. That's 1.962. So we can somehow think like maybe it should be enough already. You know, if I use margin of error equals to 1.962 times 3.74 over square root of 860, will this be reasonable? Let's see, 1.962 times 3.74 divided by square root of 860. I get 0.2502. It is still not less than 0.25. It's still not less than 0.25. Okay, so what I will do next is to increase the number of sides here. Okay, notice that I use this as a temporary only. I use this as a temporary only. Okay, now then this is the thing. Okay, given that I have 860, I will use, instead of 1.96, let me use 1.962 or 1.965. Okay, the number that we get there. 1.965 is correspond to if the degree of freedom is 500, and this is the degree of freedom of 1000. Okay, now let me continue with that assumption. Now this is my updated n. My updated n here, I use 1.965 times 3.74 square over 0.25 square. This will give me a better value. Now 1.965 square times 3.74 square divided by 0.25 square. That gives me 864.14. Now this may be an overkill. I'm sorry, 5 here. This may be an overkill, right? Okay, this may be an overkill, but well, this will be a reasonable one, right? Let's check. E equals to 1.965 times 3.74 over square root of 864. 1.965 times 3.74 divided by square root of 865. Now this is 5 here. I get 0.2498, which is confirmed less than 0.25. Okay, so we will use n equals to 865. Let me tell you what is the actual problem. We don't have a starting point of n. Okay, so we use the normal distribution to approximate what is my the number of data. Okay, now then using this 860, then I look at my t distribution table to find what is the critical value. Okay, because without the degree of freedom, without the number of data, we cannot find this one. Okay, we cannot get this 1.965 here. Okay, so in fact, you can actually omit these steps here. The first checking, you know, you can omit that. Just use that 860. Okay, use that 860 and go on to the updated number of data. Okay, but this time you use the new t critical here. Okay, and then you compute, you get that number. Does it make sense? Now when I check, yes, it is within the margin of error that I want. Therefore we use n equals to 865. Okay. Now I show you the checking here to show you that if you use this number in the margin of error, it doesn't match, because originally we assume 1.96 as our critical value. Okay, but we're supposed to use t distribution, right? Because we don't know the population standard deviation. We know the population standard deviation. I check it with the conservative or even the most loose number. Both of them does not satisfy. Okay, now in the real test you should do it this way. This is what the work's supposed to look like. Okay, using this 860 you find the t, right, from t distribution, and you get that 865. You update your number right now. You need to get 5 extra data, and then when you check the margin of error, yes, it is within the desired margin of error. Therefore we'll use 865. Okay, now I wonder if this is actually workable with 864. Now notice if I use 864, it doesn't work. You see, if I use 864, it is still greater than the margin of error, desired margin of error. You see what I mean? Okay. Did I? Oh, I missed the decimal point there. It's supposed to be point here. It is still more than 0.25 margin of error, so we really need this 865 instead. Okay, now this question is harder than supposed to be, but this is actually the actual problem in our real situation. If you don't know how many data you need to have, what do? We assume the normal distribution first. You use z-score to get the initial number, and then you plug it into the t. Okay, and then you get that one. Now then from here you try to use a number less than that, maybe 864. Will that work? If it works, try 863 all the way down to 860. Now in this case, when I try 864 here, it is already greater than 0.25. Therefore I really need a minimum of 865. Okay, now this is from fall 2011 math 227 test 3, number 4 in my test, number 8 in Melanie's test.